In neuroscience, there is a powerful idea called predictive coding. The idea is simple. Our brain does not just react to the world. It constantly builds an internal model and uses it to predict what will happen next or fill in missing information. This idea works extremely well in language models. Large language models predict the next token, and by doing so, they learn rich representations of language. But when it comes to sensory data, like images and videos, prediction is not so straightforward. Predicting pixels directly often forces the model to focus on low-level details like texture or noise instead of meaning. This is where Joint Embedding Predictive Architecture or JEPA comes in. JEPA brings predictive code into vision but with the one key change. Instead of predicting pixels, it predicts latent representations. At a high level, JEPA uses three components: a context encoder, a target encoder, and a predictor. First, we take an input like an image or a video and apply strong masking. Only a small visible part is given to the context encoder. The context encoder produces representations from this partial view. These context representations are then fed into a predictor whose job is to predict the representations of the masked regions. The target encoder processes the target view and produces the representations that the predictor is trying to match. Importantly, the target encoder is not trained directly. Instead, it is updated as an exponential moving average of the context encoder. This makes the targets stable and helps prevent representation collapse. Now, things become more interesting when we move from images to videos. Videos are highly correlated in time. If we only mask a few frames or small regions, the model can cheat by using short-term correlations and motion continuity. It can predict without understanding the actual semantics. To avoid this, JEPA uses spatiotemporal masking. Large portions of the video are masked both in space and time. The model may see as little as 10% of the video and still has to predict meaningful representations for the rest. Both short-range masks and long-range masks are used. Short-range masks remove many small patches, while long-range masks remove entire chunks across time. This forces the model to learn objects, actions, and motion patterns instead of relying on local cues. To process videos, the input is first divided into spatiotemporal patches, often using 3D non-overlapping convolutions. These patches are flattened into tokens and fed into standard vision transformers. Training is done by minimizing the distance between predicted embeddings and the target embeddings using an L1 loss or a cosine loss in representation space.